come back now to an application problem that's going to involve arc length. We have two cities, Lincoln, Nebraska and Dallas, Texas, that have, I believe it's the same longitude, but have different latitudes. So it says Lincoln, Nebraska is located 40.3 degrees north latitude, 96.7 degrees west longitude. Well, I think I got those backward, but we'll find out here in a second. And Dallas, Texas, which is located 32.8 degrees north latitude, 96.7 degrees west longitude. It says, assuming that the radius of the Earth is 3,960 miles, find the distance between the cities, and we're going to round to the nearest mile. So since they have the same longitude, I'm going to take the difference in the latitudes. I try to draw a diagram of this. Here's Lincoln, here's Dallas. This is further north, and we have to come down. It looks like the difference here, actually, I think I have that written down wrong. I think that's 40.8. Yeah, 40.8. I'll make that look like an 8 there. And so what I'm going to do is I'm going to take the difference in the latitudes here, 40.8, 32.8, well, that was convenient. Comes out to be 8.0, 0 degrees, and I'm going to find this arc length here because I know that this angle is 8 degrees. And since this angle here is 8 degrees, I can find this using that my distance here of my arc length would be theta over 360, which would be, because I'm doing degrees, this isn't degrees, over 360 times 2 times pi times my radius, which is approximated at 3,960 miles. So let's see, now I got to get Mr. Calculator out here. But if I take the calculator and if I multiply all this out, I get 552.92. That would be the arc length, and it is in miles. So to the nearest mile, the distance between the cities is 553 miles. Remember, with a story problem, you should write your answer out in a short sentence. There was really no work to show here other than doing the arithmetic on a calculator and remembering the round. Okay? Next one up, kind of a key idea in that when we talk about radian measure and such, we like to also talk about angular and linear speeds. Now, there's no real good way for me to, to try to tell you what this is pictured, because most of you probably don't know what a phonograph is or a record, but I'm going to try to represent a record here. And what we used to have as kids is we'd have a record, we'd put it on, and it would spin, depending on the size of the record, at various rates of spin. The smaller records, the 45s, would spin around 45 times, 45 complete revolutions in a minute, or 45 RPMs. The bigger records, the LPs, would spin at 33 1/3 revolutions per minute. Well, those types of speeds, 45 revolutions per minute or 33 1/3 revolutions per minute, or the old, really old records that would go at 78 and spin around, those are what we refer to as angular velocity. It's how fast the angle is changing, how fast it's spinning. Now, if you had a little dot, and I'll put it right here with an X, of fuzz on the end of the picture, and you watch that white piece of fuzz on that black record spinning around and around, and I grew up in a small town, there wasn't a whole lot of entertainment, so this was actually kind of fun to do. And watch that thing spin around. It was traveling the circumference, the distance, every revolution. So it would be considered, we could watch how far that little piece of fuzz traveled. That was considered a linear speed, even though it was going around in a circle. Because normally when we think of linear speeds, we think of a line. But if you can picture the line and this thing spinning as it goes, so that this is the X, so that this is the X, so that this is the X, it's spinning around, it will travel one complete circumference in one revolution. So we could figure out also the linear speed, and that's what I wanted to talk about, angular and linear speeds. It says here, if a point on a circle, like my piece of fuzz on the record, of radius r, moves through an angle of theta radians in time t, the angular and linear speeds of the point are defined this way. Angular speed is, now that's the lowercase letter, Greek letter omega. Looks kind of like a W with some curls to it. Omega is equal, this is our angular speed, omega is equal to theta divided by time. This is in radians. And then in this case, the linear speed was the or v for the velocity here, was equal to the arc length divided by the time. Now remember, arc length is r theta, so we could have also thought of this as r theta divided by the time, but since omega is theta over, omega is theta over time, and this is theta over time, we could think of this as r times omega. So I'm going to do an example here, looking at angular and linear speed involving a bicycle wheel. The bicycle wheel rotates at 2 revolutions per second. We're going to find the angular speed, which is omega, right, is equal to our angle in radians divided by our time. Well, if we're looking to get our answer in radians per second, we have to change 2 revolutions into radians. So we have 2 revolutions in 1 second, and we know that 2 pi is 1 revolution. So what we have here with the little dimensional analysis is that we have 4 pi radians in 1 second, or 4 pi radians per second. And that would be considered the angular speed. Now, how fast does the bicycle travel? Because the bicycle travels kind of like the idea of what my circle is doing here as it's spinning, as it's moving down. If the diameter of the wheel is 2.2 feet. So what we're going to do now is we're going to take and we're going to find the velocity here, the linear velocity. The linear velocity is equal to the radius of the wheel, which is this is to the nearest tenth, 1.1 feet, half the diameter, times the omega, which I just figured out over here, was 4 pi radians per second. So this is in feet, and this is times radians per second. Well, if I multiply 1.1 times 4 pi, I get 4.4 pi. Hopefully you can still see that okay. And that's going to be in feet per second, or this is approximately, to the nearest tenth, 13.8 feet per second. So that's how fast your bicycle with that size wheel and that rate of rotation is traveling in feet per second. Now there's one more topic I want to talk about, and it actually goes right along with the idea of arc length, and that is finding the area of a sector. Now a sector, remember, kind of looks like a piece of pie. You have a circle, you have 2 radii. This region right here, that geometric shape, that is called the sector of a circle. And you can find the area of a sector by using either one of the following 2 formulas, depending on what your angle measure is. You can use, for radians, 1/2 r squared theta. Now remember, r theta is arc length, so it's also the same as 1/2 rs. Or if in degrees, you can use theta divided by 360 times pi r squared. And both formulas are found the same way. It's the angle out of the complete revolution, out of 2 pi here, out of 360, times the area of the circle, pi r squared. Now we have an example here. It says a sprinkler rotates through an angle of 120 degrees and sprays a distance of 30 feet. To find the amount of area watered. Well, what we have here is a circle, a circular shaped sprinkler. You know what I'm talking about here in Las Vegas anyway. And the sprinkler is going to go through about 120 degrees like this. And it sprays out a distance of 30 feet. So my angle, interior angle there, my angle of my sector is 120 degrees, and of course the radius here is going to be 30 feet based on this measure. To find this, I'm going to use this guy right down here, and I'm going to find that the area watered is equal to 120 divided by 360 times pi times 30 squared. Now this is 1/3 and this is 900, so this would be 300 pi, and this is going to be square feet, but it says it wants the answer here to the nearest whole number, so I'm going to multiply 300 times 3.14159 and round to the nearest whole number, and this would be approximately 942 square feet. Okay, which is the answer to the problem there. So there's a lot of information in this very first section on trig, and we haven't even really touched the trig yet. We're just talking about angles and some of the stuff that we can do with arc lengths and with areas of sectors. By the way, there may come a problem that you'll be working on where they will ask you to find the area of this shape right here, which is called the segment. A segment of a circle. And what you do there is you find the area of the sector and then you subtract from that the area of the triangle. It's kind of like you're finding the area of the ice cream, and you do that by taking the whole cone and then subtracting just the cone part and leaving just the ice cream part that's got kind of a little squiggle there. Just hopefully a helpful little hint if you run across a problem asking for the area of the sector. Practice, practice, practice.